Welcome to another lesson from Transparent Physics, and today we are going to continue our discussions of dynamics, specifically in the context of the discussion of mass versus weight, which is not the worst thing that you're going to be dealing with in introductory dynamics, but it is a possible point for confusion and could cost you a couple points if you're not careful. In this lesson, we are going to distinguish the difference between mass and weight. We'll show you how to calculate weight with the use of a formula. And we'll also sort of pull out the focus a little bit and talk about why heavier objects don't fall faster, why more weight doesn't mean more acceleration. As we have talked about in some previous lessons, we do have to be a little careful when physics words overlap with everyday common usage words. In this case, the idea of weight. The Bloom County comic strip here does show us the typical idea people think about when we're talking about weight. And the weight loss industry, I checked, is approximately a $33 billion a year industry in the United States. So there's lots of money to be had for talking about weight loss. But realistically speaking, that might be a little bit off, because technically if you want to lose weight, we really should be focusing more on mass than weight. And so what's the difference between those? Well, let's find out. Let's compare some properties of mass versus weight. You know, things are about to get real when we break out a data table. So let's fill this up with some good physics. Starting with mass definition, the idea of mass is that it's a fundamental property of an object. It's part of what an object is. And I can take an object to the moon, I can take it to Pluto, I can take it to Jupiter, and the mass is the mass is the mass. It is determined by the amount of matter in the object, and generally I tend to think of matter really as protons and neutrons. Electrons have mass, but I think it's like 99.9 something percent of your mass is the protons and neutrons that make you up. Electrons account for actually a very, very small fraction of your total mass. So if you want to change your mass, add or subtract some protons or neutrons to the object. On the other hand, weight is more complicated. Weight is a phenomenon, basically. It's when you take a mass and you put it in an area of gravitational attraction or a gravitational field. That gravitational field will pull on the object, creating a force. How that happens is another issue entirely. We're not going to discuss that in this lesson. It's just recognizing that gravity pulls objects towards each other, and that force of gravity we call an object's weight. And this weight can be calculated by taking the product of two measurements, the object's mass and the strength of the gravitational pull. Mass we just discussed, and the strength of gravitational pull is often sort of quantified in the acceleration due to gravity, aka little g. And little g generally is constant if you're staying on Earth. We treat it that way in introductory physics. Obviously, the universe is a big place, and in a lesson on gravity somewhere down the way, we'll talk about how to calculate little g in other places. But for now, we don't need to worry about it. G is 9.8 meters per second squared. Mass is a scalar quantity. Scalar quantities have magnitude only. There's no direction. If I say an object has a mass of 6.52 kilograms, I'm done. I don't need to describe anything else about it. That is the measurement in question. Weight, being a little more complicated, weight is a force. Forces are vectors. So if we want to completely describe a vector, we need a magnitude and a direction. And generally speaking, weight acts down. In terms of units, these are important to pay attention to because they can help keep you on track whether or not you're assigning the right measurements to the right variables, because mass and weight are similar to a lot of introductory physics students. It is easy to plug one into the wrong place and end up with the wrong answer. So units take on outsized importance for this particular topic. In the metric system, in the SI system, we use kilograms as the base unit of mass. Some people might ask, well, why don't we use grams? Grams are too small, really. So we use kilograms instead. The metric unit for force is a Newton, as was introduced in some earlier lessons as well. And just as a reminder, whenever you have a unit that's named after a person, we do not capitalize that unit when it's written out as a word, although you do capitalize the first letter when you abbreviate it. So newtons has a lowercase n, but you write it with a capital N when you're using it as a unit for a measurement. And then on the English side of things, always more complicated, the unit for force in the English system is a pound. And so pounds and newtons serve similar roles. But while the metric system has a unit for force and a unit for mass that are fairly, regularly understood, the English system does have a unit for mass, but I probably assume most of you have never heard of it before. It is the humble slug. So slug is the metric unit for mass. If you're interested, a slug is 32-ish, I think, pounds, roughly speaking. So there you go. The English system does have a unit for mass, and like much of the English system, it's kind of silly. And as we are ready to move into the more technical aspects of the discussion, little public service announcement about why this matters again. Casual conversation, it doesn't really matter. If you're talking with a neighbor and you exchange the words mass and weight with each other, I don't know, mass doesn't come up all that often, but I don't think they're really going to call you out on it. But in physics, mass and weight are very different from each other. So we do need to attend to this with appropriate detail, because if you get a initial measurement as 5 kilograms and you plug that in for the weight, you're going to end up with the wrong answer. So we have to be careful that we understand what measurements go with what definitions so that we don't mess up our math problems. Solving for weight itself is pretty easy to do. The equation is W equals mg. And this equation may look a little bit familiar because it's very similar to F equals ma. F equals ma is sort of a generic equation, and W equals mg is a more specific version of that for weight. As we noted when we first discussed F equals ma, the units, weight is a force in newtons, m mass kilograms, and g is an acceleration meters per second squared. So a newton is the equivalent to a kilogram meter per second squared, as it is whether we're talking about weight or not. When we are looking to assign a number to g, most introductory physics courses say 9.8 meters per second squared is fine, acting downward. Some people say 9.81 meters per second squared. Not a big difference between those values, and it does act downwards. I'm going to use the word acting downward right now instead of the negative sign. The negative sign I find is a little bit of an issue at this point in the course. I don't like to automatically say weight is negative 400 newtons. And that really is just saving ourselves a headache a little later in the course when we start looking at forces in two directions and we start using vectors. We generally want to consider weight to be a magnitude, and then what direction is it acting in. If we just automatically tack that negative sign on all the time, it can lead to some issues a little bit later in the course. And so generally speaking, I just like the magnitude. Like when I'm talking about my weight, I don't say, hey, I am negative 195 pounds. You don't say that. Weight is implied to be acting downward, and if we need to, we can put the negative sign in. And the exception to that I do use is G. Historically, I only set default negative in the Scooby equations, back in the kinematic equations. So when you're dealing with Fred and Velma and Daphne and Shaggy, G in a vertical scenario, set that as negative and just run with it. But when you're dealing with forces in dynamics, I like to leave G just as the magnitude and then assign the direction as needed to later. And no good discussion of weight would be complete without trying to answer the question, do heavier objects fall faster? And again, you may have heard of the story of Galileo dropping two different massed objects off the Leaning Tower of Pisa, and that they fell at the same rate. Whether or not that actually happened or not, the idea is that we assume that heavier objects should fall faster. That's actually not the case. I will qualify that slightly. It is not true as long as air resistance is insignificant. Obviously, if I take a uncrumpled sheet of paper and a golf ball, the golf ball is going to hit the ground first. A feather versus a penny, the penny is going to hit the ground first. The reason that the other object hits the ground later is not because gravity, it's because of other forces acting on it. So if we can eliminate air resistance, then all objects are going to fall at the same rate. And this is a little tiny clip of a BBC show. This is inside of a giant, basically vacuum room where they can suck all the air out of it. And you can see they've got a heavy metal sphere and a couple feathers, and they drop them at the same time, and they fall at the same rate and hit at the same time. So the only reason feathers would fall more slowly is because there's air interacting with them, slowing them down, and they are more significantly affected by that than the heavier object is because their mass is lower. And you know, the amount of force depends on the aerodynamics of the object, and it gets pretty complicated. So at an introductory level, we will ignore air resistance. So every set of objects is going to behave this way unless your problem otherwise says. So why when we take a look at the video, why does the heavy ball fall at the same rate as the feathers? If we dig back a little bit to Newton's second law, we remember that the acceleration of an object is equal to the net force divided by the mass. And if we eliminate the air resistance from the chamber, then the only force acting on the objects when they're released is their weight. So there's the weight acting on the red metal sphere, and there's the weight acting on the set of feathers. Now, no doubt about it, the red ball is absolutely heavier than the feathers. And as an object's mass increases, the amount of weight pulling on it increases as well. So they are proportional to each other. However, when you get that larger force, you're also kind of paying for it as well, because heavier objects are also harder to accelerate. So while the feathers have less mass, so there's less gravity pulling on them, they are less massive, so a smaller force can result in a larger acceleration. The red metal sphere, it has more force acting on it, absolutely, but it also has more mass, so it's harder to push. Kind of like the difference between how hard it is to get an empty shopping cart in motion versus how hard it is to get a full shopping cart in motion. So the inertia of the heavier object actually slows down the acceleration, if you want to think about it that way, such that no matter how much extra force you're gaining from your weight, the extra inertia associated with that mass actually makes it so all objects do fall at the same rate. Legal disclaimer: when air resistance is insignificant. So to conclude, the argument that people make when they want to lose weight is generally them saying they want to lose mass. You can lose weight by going to the moon, but when you look in the mirror, you're still going to look the same. That's really probably not what we're ultimately interested in. The weight is just an easily measurable side effect of your mass. So generally, when we want to lose weight, we actually want to lose the mass that's the reason for that weight. And in casual conversation, we can get away with that because weight and mass are proportional to each other by the value g. So if we lose mass, then we're losing weight, and we got to our end goal. But where casual conversation allows us to sort of use weight when we're referring to mass, the formulas are not as lenient. You have to be very careful when you're getting ready to plug values into equations that you are plugging the correct term in. You might be given the mass to start, and you might have to solve for the weight. You might be given the weight, and you need to solve for the mass before you plug it into a formula. So take your time when mass and weight are on the board. Check your units. Weight is going to be measured in newtons, mass is going to be measured in kilograms, and make sure you put the right value in the right slot. At this point, I'm just going to pause, take a nice long sip of tea. I'll let you stop and think maybe if you want to do something right now while I'm just enjoying my tea. There we go. As always, I appreciate your time in tuning in, and I hope I've managed to make things a little clearer for you on this lesson of transparent physics.